There is an animal that produces 76 different antibiotics from its skin, not in a laboratory, not in a factory, from its body continuously, every hour it is alive. There is a folk practice, documented across Russia and Finland for over 2 centuries, in which this animal was placed in fresh milk to prevent spoilage. There is a study, published in 2012 by researchers at Moscow State University, confirming that these skin-secreted compounds kill Staphylococcus aureus and Salmonella enterica with effectiveness equal to prescription drugs. There is a $1 trillion dairy industry, a $78 billion refrigeration industry, and a pharmaceutical sector spending billions searching for new antibiotics. As resistance kills over 1 million people a year, and there is a frog, a common brown frog, sitting in a pond, manufacturing the solution to all 3 problems, for free. A family milks the cow at dawn. There is no electricity. The first home electric refrigerator will not be invented until 1913 by Fred W. Wolf in Chicago, and it will cost $900, more than most Russian farming families earn in a year. Ice houses exist, but they are for the wealthy. Cellars help, but in a Russian summer, even a cellar cannot hold temperatures below the critical threshold. And the critical threshold is this: milk left at room temperature spoils within 2 hours. The United States Dairy Council confirms that above 40 degrees Fahrenheit, bacteria in raw milk double every 20 minutes. Within 24 hours, the milk is curdled, sour, and potentially dangerous. By 48 hours, it is a bacterial colony. In a world without refrigeration, fresh milk is a race against biology, and biology always wins. Except in certain Russian and Finnish villages, it did not. These families took a live brown frog, Rana temporaria, the European common frog, and placed it directly into the bucket of fresh milk. The frog sat in the milk. The milk stayed fresh. Not for hours, for days. Sometimes for over a week. The family drank the milk, cooked with it, fed it to their children. The frog was unharmed. It was removed, returned to the pond, or kept for the next bucket, and the cycle repeated. To modern ears, this sounds like superstition. Like burying a horseshoe under your doorstep, or hanging garlic to ward off illness. Western scientists dismissed it for decades as exactly that. An old wives' tale from the Russian countryside, charming, but scientifically meaningless. They were wrong. In 2012, a team of researchers at Moscow State University, led by T.U. Samgina and colleagues, conducted a comprehensive analysis of the skin secretions of Rana temporaria collected from the Moscow region. Using nano-HPL CSE Orbitrap mass spectrometry, one of the most precise analytical instruments in modern chemistry, they identified 76 distinct antimicrobial peptides in the skin secretion of this single species. 76, a previous study had found 21. This new analysis tripled the known chemical arsenal of one frog. The study was published in the Journal of Proteome Research, a peer-reviewed journal of the American Chemical Society. The PubMed reference is 23,121,565. You can read it today on February 6, 2013. The American Chemical Society issued a formal press release titled "Frog in Bucket of Milk Folklore Leads to Potential New Antibiotics." NPR covered it on December 17, 2012. Under the headline "Scientists Look for New Drugs in Skin of Russian Frog," Atlas Obscura published a detailed feature in April 2018. Confirming the practice and the science behind it. This was not a fringe discovery buried in an obscure journal. It was announced by one of the most authoritative scientific bodies on Earth and reported by mainstream international media. Now let me explain what these peptides actually do, because the mechanism is what transforms this from a curiosity into something that should change how you think about biology, medicine, and the entire pharmaceutical industry. The 76 peptides identified in the skin of Rana temporaria belong to several families. The most studied are the Brevinin family and the Temperin family. Brevinin 1-TB is one of the most potent. A 2024 study published in the journal, Molecules confirmed that Brevinin peptides work by directly penetrating bacterial cell membranes. They are amphopathic, meaning one side of the molecule is attracted to water and the other is attracted to fat. This allows them to insert themselves into the lipid bilayer of a bacterial cell membrane, the thin fatty wall that holds the bacterium together. Once inserted, they do not gently nudge the membrane apart. They punch holes in it. Multiple peptide molecules aggregate on the membrane surface, rotate, and drive through the lipid layer, creating pores. The bacterial cell contents DNA, proteins, enzymes, everything leak out through these pores. The cell collapses and dies. The entire process takes minutes. The critical detail is this. The original 2012 study by Samgina and colleagues tested these peptides against Staphylococcus aureus and Salmonella enterica cerevar typhimurium, two of the most common and dangerous foodborne pathogens. The inhibitory effects were, in the researchers' own words, equal in scale to those of conventional prescription antibiotics. Equal in scale, not weaker, not comparable, equal. And here's why that finding carries weight far beyond a bucket of milk. Staphylococcus aureus is responsible for skin infections, pneumonia, endocarditis, and sepsis. Its methicillin-resistant variant, MRSA, is one of the most feared pathogens in modern hospitals. Salmonella enterica causes an estimated 1.35 million infections in the United States alone each year, according to the CDC. Together, these two organisms represent some of the most persistent threats in food safety and clinical medicine. The peptides on the skin of a common pond frog kill both of them, with effectiveness equal to the drugs we spent billions developing, and the frog produces them continuously. It does not need a factory. It does not need raw materials shipped from overseas. It does not need quality control or batch testing. Every hour that the frog is alive, its granular glands secrete a fresh cocktail of antimicrobial peptides onto its skin surface. This is not a one-time chemical dump. It is a living, self-renewing pharmaceutical production line. The reason frogs evolved this system is simple and brutal. Rana temporaria lives in some of the most bacteria-rich environments on Earth. Ponds, marshes, wet forest floors, stagnant water. These habitats are swarming with bacteria, fungi, and parasites. The frog has no scales, no shell, no thick hide. Its skin is thin, moist, and permeable. It actually breathes through its skin. Without a chemical defense system, it would be consumed by infection within days. So evolution gave it a pharmacy. 76 compounds, each targeting different classes of microorganisms, each working through slightly different mechanisms, making it nearly impossible for any single pathogen to develop resistance. This is the exact opposite of how modern antibiotics work. We develop one drug. Bacteria evolve resistance to that one drug. We develop another. They evolve again. The frog deploys 76 simultaneously. The bacteria cannot outrun all of them at once. Since 1987, researchers have identified over 1,000 antimicrobial peptides from the skin secretions of amphibians across more than 300 species. A 2020 study published in PMC analyzed 1,000 of these peptides. A comprehensive review in Axe Chemical Reviews cataloged over 2,000 peptides from amphibian skin. The frog is not an anomaly. Amphibians as a class are the single richest source of novel antimicrobial compounds on the planet, and the pharmaceutical industry knows it. A 2025 paper published in Trends in Biotechnology by researchers at the University of Pennsylvania's De La Fuente lab described frog-derived synthetic peptides that display anti-infective activity against gram-negative pathogens, the class of bacteria that includes E. coli, Pseudomonas, and Klebsiella, and which are notoriously difficult to treat with conventional antibiotics. The researchers called the results promising preclinical antibiotic candidates. A 2025 study in PMC described rational design approaches to enhancing frog skin antimicrobial peptides for clinical use. A review published in MDPI Antibiotics in 2025 positioned frog skin peptides as dual-action weapons against both infection and cancer. Frontiers in Cellular and Infection Microbiology published a 2026 paper describing antimicrobial peptides as natural templates for next-generation antibiotics. This is not folklore anymore. This is an active pharmaceutical research frontier. The frogs are being studied in the most advanced laboratories in the world as a potential answer to the single most dangerous medical crisis of the 21st century. Antibiotic-resistant infections killed an estimated 1.27 million people globally in 2019. That number comes from a landmark study published in The Lancet and is cited by both the WHO and the CDC. An additional 4.95 million deaths were associated with antimicrobial resistance in the same year. The WHO has described antibiotic resistance as one of the biggest threats to global health, food security, and development today. The antibiotics we have are failing. Bacteria are evolving faster than we can develop new drugs. The standard pharmaceutical pipeline takes 10 to 15 years and over $1 billion to bring a single new antibiotic to market. Meanwhile, a frog produces 76 of them from its skin, for free, every day of its life, and has been doing so for millions of years without a single documented case of bacterial resistance. Now let me put the economics in perspective. The global dairy product market is worth approximately $1.006 trillion as of 2025. According to Fortune Business Insights, $1 trillion, the entire edifice of pasteurization, ultra-high temperature processing, cold chain logistics, refrigerated trucks, temperature-controlled warehouses, and your home refrigerator exists, in large part, to solve one problem: keeping milk from spoiling. The global refrigerator market alone is worth $78.39 billion in 2025, according to Fortune Business Insights. The average American household spends between $57 and $111 per year on electricity just to run the refrigerator. According to data from CNET IGS Energy and reviewed, that refrigerator runs 24 hours a day, 7 days a week, 365 days a year. It never stops. From the moment you plug it in until the day it dies, it consumes electricity. The average lifespan of a refrigerator is 13 years. Over its lifetime, a single unit costs between $740 and $1,440 in electricity alone, not including the purchase price. A frog costs nothing. It lives in the nearest pond. It runs on insects. Now, I need to be absolutely clear about something, because this is where the story requires honesty. I am not telling you to put a frog in your milk. Do not do that. This script is about the science. It is about the history. It is about what the peptides are and what they mean for the future of medicine. It is not a DIY instruction manual. There are critical reasons you should not replicate this folk practice at home. First, wild frogs can carry parasites, including trematodes and nematodes, that could contaminate food. Second, amphibian skin can harbor Batrachochytrium dendrobotitis, a chytrid fungus responsible for devastating frog population declines worldwide. Handling wild frogs risks spreading this pathogen. Third, some frog species carry salmonella on their skin. Ironically, the very pathogen the peptides fight internally is sometimes present externally from the frog's environment. Fourth, in many jurisdictions, capturing wild amphibians is regulated or prohibited due to conservation concerns. Fifth, raw milk itself carries inherent risks, and no folk method replaces proper pasteurization and refrigeration for food safety. The Russian villagers who practiced this were operating within a specific ecological and cultural context. They used a specific species. They used raw milk from their own cows. They had no alternative, and they accepted risks that modern food science has spent a century learning to eliminate. The point of this story is not the bucket, it is the frog. Because what is sitting on the skin of Rana temporaria and on the skin of hundreds of other amphibian species across the planet is a library of pharmaceutical compounds that humanity has barely begun to read. Over 1,000 antimicrobial peptides have been identified from amphibian skin since 1987. Over 2,000 are cataloged in review literature. Each species carries a different combination. Each combination targets different pathogens through different mechanisms. The diversity is staggering. And here is what makes this urgent. Amphibians are disappearing. The International Union for Conservation of Nature reports that over 40% of amphibian species worldwide are threatened with extinction. The chytrid fungus alone has driven at least 90 species to extinction and caused catastrophic declines in over 500 more. Habitat destruction, climate change, pollution, and disease are erasing amphibian populations faster than at any point in recorded history. Every species that disappears takes its unique peptide library with it, permanently. Once a frog species goes extinct, those compounds are gone. They cannot be reconstructed. They cannot be guessed. They are lost the same way a burned manuscript is lost completely and forever. We are losing potential antibiotics, potential antifungals, potential anti-cancer compounds, and potential solutions to the drug resistance crisis every time a pond is drained, a wetland is paved, or a forest is cleared. The Russian brown frog, Rana temporaria, is currently listed as least concern by the IUCN, meaning its population is stable. It is widespread across Europe, from the Pyrenees to the Urals and into western Siberia. It inhabits damp woodlands, meadows, and garden ponds. But even common species are not immune to the pressures that have already wiped out their relatives. The pharmaceutical industry is spending billions trying to synthesize what frogs produce naturally. Researchers at the University of Pennsylvania are building synthetic analogs of frog peptides in the lab. Teams across Asia and Europe are testing modified versions against MRSA, Pseudomonas, and gram-negative superbugs. Clinical pipelines are forming, patents are being filed, and the source material, the living, breathing, peptide manufacturing frog, is sitting in a pond that someone might fill in next year to build a car park. Let me bring this back to the milk bucket. For over 200 years, Russian and Finnish villagers solved a problem that a trillion-dollar industry now manages with electricity, machinery, and infrastructure. They did it with a frog. They did not know why it worked. They did not need to know. They observed that milk with a frog in it stayed fresh longer than milk without. They repeated what worked. They passed the knowledge to their children. And for generations, it was sufficient. Then the modern world arrived. Refrigerators replaced cellars. Pasteurization replaced folk methods. Industrial cold chains replaced local solutions. And the frog was forgotten. Not because it failed, because something more expensive replaced it. The modern refrigerator was invented in 1913. Mass production began in 1918. By the mid-20th century, the refrigerator was standard in every Western household. The folk practice of putting frogs in milk disappeared within a single generation. It became a footnote, an anecdote, something your great-grandmother might have mentioned and you would have laughed at. In 2012, Moscow State University proved that your great-grandmother was right. 76 antimicrobial peptides, effective against Staphylococcus aureus and Salmonella enterica, equal in scale to prescription antibiotics, produced continuously by a living organism that costs nothing to maintain, confirmed by peer-reviewed research published by the American Chemical Society, reported by NPR and Atlas Obscura, now being studied by some of the most advanced pharmaceutical laboratories on Earth as a blueprint. For the next generation of antibiotics, a frog in a bucket of milk. In a Russian village, 200 years ago, they were not being superstitious. They were practicing biomedicine. They just did not have the vocabulary to name what they were doing. And now, when 1.27 million people die every year from antibiotic-resistant infections, when the drugs we have are failing faster than we can replace them, when pharmaceutical companies spend over $1 billion in a decade to develop a single new antibiotic, that bacteria will outsmart. Within years, the answer might have been sitting on the skin of a frog this entire time. 76 compounds, 1 animal, 0 resistance, documented in millions of years of evolution. Nature solved the antibiotic problem before we knew antibiotics existed. We just stopped listening, and a trillion-dollar industry had no financial reason to remind you.